morning, dear students. I am Dr. N. Ganesan, Department of Physics from Erode Engineering College. In this valuable morning, I am going to tell something about superconductivity. Before to see the topics, the topic that I prepared for you is listed on the board. We shall see one by one. First, we shall give some introductions about the superconducting phenomena. Usually, this was introduced by Dr. H.K. once in the year of 1905. After the inventions of superconducting, there are a lot of revolutions takes place in the new engineering materials. See, superconducting means, in the name itself it shows that what the difference between the conducting material and superconducting material. In superconducting material, only free electrons contribute for conductivity. In the case of superconducting material, the same normal conductor will not act as a superconductor, and superconducting exists because of the formations of Cooper pair they told. Even they proved it. Before to see it, we shall see what is conductivity, what is resistivity. They said in superconducting material there is no resistance. The resistance disappears. That means before to see how the resistance disappears, we shall see what is resistance, where it comes, what are the reasons for it. See, resistance. What is resistance? Suppose if you are traveling in two-wheeler, to control our speed, there are a lot of speed brakes that control our speed. In the same way, suppose if it is a conductor, rectangular slab conductor, the slab can be split into large number of slices like bright slices. These slices can vibrate. The vibrations of the slice depends upon the temperature. If temperature is more, the vibration is more. So electron cannot easily transfer from one end to another end. Because of this lattice vibrations only, the electron get resistance. So in a normal conductor, even at the room temperature, the lattice start to vibrate. So it gets resistance. So you might understand that the resistance exists because of lattice vibration. So here you can come to the conclusion that lattice vibration is the main reason. Lattice vibration is the main reason for the existence of resistance. Even the lattice vibration is directly proportional to temperatures. In the superconducting phenomena, the resistance disappears, not in the room temperature. It takes place at a very low temperature. See, it is in this graph. I will tell the relationship between the temperature and resistivity later. Before that, I like to give small introductions about the resistance. The resistance is directly proportional to length of the conductor and inversely proportional to area of cross sections. Suppose we are using the cables we are using in our homes. The shape is in a cylindrical form. So it can be drawn like this. See, the resistance is more when the length of the conductor is more. The resistance is less when the area of crosses is the area of crosses is more, the resistance will be less. Because if area is more, means electron can easily travel from one end to another without disturbing others. To remove these proportionality constants, we are putting equal sign and some constant. This is called resistivity. So we can bring this left side like resistivity is directly proportional to resistance and area of cross section inversely proportional to length. So we might do something about what is resistance and what is resistivity. When the resistance disappears, I said the resistance disappears at a low temperature. What's the reason? At low temperature, lattice vibration stops. If lattice vibration stops, means there is no disturbance to the flow of electrons, so the electron can easily flow. This is the concept behind the superconducting phenomena. Okay. Let us see what are the material exist in the superconductor. If I ask you, give some examples for best conductors, means you will tell even iron also. But the same material will not show the superconducting phenomenon at low temperature. See, scientists listed the list of superconductor for our understanding purpose. The list are 10. They exist superconducting phenomena at 3.7 Kelvin, indium 3.4 Kelvin, tandem 4.5 Kelvin, vanadium 5.4 Kelvin, lanthanum 6 Kelvin, like this. See, before to understand where we are studying, I am drawing a small graph for our understanding purpose. Here this is a Celsius scale bottom. We are familiar with the Celsius scale, we are not familiar with the Kelvin scale. To make the interrelations between them, I draw this small graph for you. See, minus 273 degree is the lowest possible obtainable temperature by us. In the Celsius scale, there is a minus as well as plus, both are present. Whereas in the Kelvin scale, only positive states are present. Here I take 0 degree Kelvin is equal to minus 273 degrees Celsius. That means, see, indium showing the superconducting phenomena at 3.4 Kelvin means you just think about around 3 or 4 Kelvin, where it will be 0, 1, 2, 3, 4 Kelvin is here. It is equal to what? Around 269 degrees Celsius, minus 269 degrees Celsius. This is called low temperature physics. Even to achieve these lowest temperatures, we have to use liquid helium or nitrogen. These are very costly. So, to relate the resistivity and temperatures, I draw this graph. Here, temperature is taken along the x-axis and resistivity is taken along the y-axis. This is a curve for normal conductor. This is a curve for superconductor. What the graph shows means that the first case, the normal conductor graph 1 shows that as temperatures decreases, see, here is the maximum temperature. Maximum temperature, the resistivity is maximum. As temperatures decreases, resistivity decreases. This means that, as I said, as temperatures decreases, lattice vibration decreases, so resistivity also decreases. That is going on true in the case of conductor also. Further, you are reducing the temperature, going, and up to minus 273 degree Celsius or 0 degree Kelvin. Even if you bring the temperature to 0 degree Kelvin, the normal conductor is showing some resistivity. That means the resistivity is not disturbed in the case of normal conductor, like silver, copper, iron, gold. Whereas in the case of superconductor like this, mercury, tin, and vanadium, diamond, these materials resistivity disappear just before or well before the absolute temperatures. For example, see, this is minus 270 degrees or 0 degree Kelvin. Here if it is 4 Kelvin means, or again 4 Kelvin means, here its resistance disappears totally. So in this state, it will act as a superconductor. See, in the case of superconductor, the temperature is more, resistivity is more. The temperature decreases, resistivity decreases. This is true as long as up to this line. After that, for a particular temperature, the resistivity becomes disappear. Suppose if you want to take value from this point means you will have x-axis value. Let it be x1, y1. It has two values. When you reduce the temperature, you will come here. Here let it be x2. What about y? It will become 0. That means resistivity disappear. If you further reduce the temperature, the resistivity further disappearing, lowering, the superconducting phenomena increasing. This is the fact behind the superconductor. In the last class we saw something about superconducting material. In the superconducting material, the resistivity becomes 0. It happens only at particular temperature, not at absolute 0 K. That means well before 0 K, some material loses the resistance. The property is studied by these scientists named as the body, Cooper and Serre. So that is why it is called BCS theory. According to this theory, they gave the explanation for the occurrence of Cooper pair. They introduced a new term called Cooper pair. Cooper pair is nothing but the formation of two electrons, the joining of two electrons. According to you are saying that electrons having negative charges, they will reflect. But they showed us to the world that the electron can join together through some medium. That electron pair is called Cooper pair. They gave the explanation for that. See, in the previous class itself I told, if it is a conductor, the conductor can be split into large number of slices like this. So these are the one slices, second slices, third slices. Only for understanding purpose, three slices are taken. First one, second one, and third one. In the middle layer, that is central lattice plane, these dots are positive ions, lattice ions. Suppose if one free electron is approaching the lattice ions, it is negative charge, it is positive charge, it will be attracted. When the electron come and attract to the positive ions means there will be sudden disturbance. The lattice will start to vibrate. That vibration is called phonon. If suppose another electron named as E2 come in this direction, it will be attracted by this lattice ion, then a greater force that of the first electron. It is attracted by the foreign lattice ion, first case. After it is attracted, if another electron comes in this direction, this second electron is attracted by the same positive lattice ion with a greater force. What does it mean? Its meaning is that when the electron 1 joins with the positive lattice ions, its positive potential increases. That is why it attracts a greater force with the second electron. At this moment, this electron 1 and electron 2 are coupled with each other through the phonon ring. This is called the Cooper pair. This takes place only at low temperature, and that temperature may be called as critical temperature. For example, niobium, I said the transition temperature is 9.5 Kelvin. Tc for niobium. 9.5 Kelvin. At 9.5 K, electron pairs are formed. Then what is the advantages? Once pairs are formed, it should give some advantages or disadvantages. Here it produces some advantages. Once the electrons are formed, they sail some distance without any resistance. That is called the coherence level. This is the explanation given by the scientists Body, Cooper and Serre. They gave the explanation for the formations of Cooper pair in the superconductor. So are you clear? Yes, sir. Okay, thank you. Next, we study something about what is superconductor. Superconductor does not give any resistance. One, the resistance disappears when the Cooper pairs are formed. When the Cooper pairs are formed at low temperature. The temperature at which the Cooper pairs forms are called critical temperature. Once Cooper pairs formed, the resistivity disappears. Next, I may ask some questions. What are the example of some superconductor? You may say niobium, vanadium, tantalum, even mercury. These are all act as a superconductors. What are normal conductors? Silver, copper, iron, gold. These are all normal conductors, but the normal conductor will not act as a superconductor. See, so we shall see some properties of the superconductor. What are the superconductor? Niobium, vanadium, tantalum, tin, lead. These are all the superconductor. So we shall see some properties of superconductor. What I said first, zero electrical resistance. This is the first and foremost properties of a superconductor. Superconductor means it does not show any resistance. Zero electrical resistance means these superconductor like aluminum, tin, lead, niobium does not give any resistance at this transition temperature. Why they don't show any resistance to you? At low temperature or transition temperature, they form a Cooper pair. Once Cooper pair formed, they travel or sail some distance without any resistance. That distance is called the occurrence length. Okay? Next. I hope that you understand. Superconductor means does not show any resistance, that is zero resistance. You know the reason for that one also. The superconductor is said, that means Cooper pair formed there. When the Cooper pair formed, low temperature. Low temperature, again particular temperature called critical temperature. At critical temperature, Cooper pairs are formed. Once Cooper pairs are formed means they can sail without any disturbance. Next one, effect of magnetic field. Even a superconductor showing superconducting property. Can we convert the superconductor into normal conductor? Means yes. A superconductor can be converted into normal conductor with the help of magnetic field. See that? Let it be a niobium superconductor. Niobium superconductor. It transition temperature DC. May 9.5 K. It is kept in a system. This is a system. Like a refrigerator, freezer. Using the system, we can reduce the temperature as our needs. Here, you are maintaining a temperature T. The T is less than TC. TC is 9.5. Then what about T? May be less than 9. Let it be 8 Kelvin. So the superconductor ring will show the superconducting property. My aim is to cancel the superconducting property of the niobium. This is niobium superconductor. Its transition temperature is 9.5 Kelvin. My aim is to cancel the superconducting property. Though you are maintaining a temperature using system less than TC. TC value is 9.5. You are maintaining a temperature T 8 Kelvin. That is T is less than TC. It is in superconducting state. No doubt at all. By keeping the same temperature, I can cancel the superconducting property with the help of magnetic field. See, this is north pole. This is a south pole. Electromagnet. If it is given to the electromagnet, by changing the potential, I can change the electric field. For certain value of magnetic field, see, the lines will start from here to here, and here. For certain value of magnetic field, the superconductor lost its superconducting property and become a normal conductor. You have to find the value for what value of magnetic field the superconductor become normal conductor. That magnetic field is called the critical field. Critical magnetic field. Then what is critical magnetic field? It is the amount of magnetic field needed to cancel the superconducting property of a superconductor, though the superconductor is in superconducting state. That is called the critical magnetic field. Let it be, let's see. It may be 0.2 Tesla, 0.02 Tesla. In that manner, it will be here. So, from this diagram, you might understand that a superconductor can be converted into a normal conductor, though it is in superconducting state, with the help of magnetic field. So, the amount of magnetic field needed to cancel the superconducting property of the superconductor is called the critical magnetic field. This is the effect of magnetic field. Here I took niobium. Transistor temperature is 9.5 Kelvin. The temperature maintained is 8 Kelvin. The amount of magnetic field needed to cancel the superconducting property be 0.04 Tesla. Let it be. The value is not correct. For understanding purpose, let it be 0.04 Tesla be the amount of magnetic field needed to cancel the superconducting property of the niobium. At what temperature? 8 Kelvin. Next, we reduce the temperature to 7 Kelvin. The transistor temperature is reduced to 7 Kelvin. Now, again, the magnetism field is varying. If you study it clearly, its value will be less than or greater than 0.3 Tesla is needed. In the first case, when we maintain temperature at 8 Kelvin, the amount of magnetic field needed to cancel the superconducting property is 0.04 Tesla. Second case, the value is increasing. Which value is increasing? Critical magnetic field is increasing as temperature is decreasing. That means, as temperature is decreasing, the superconducting nature of the superconductor increases. That is why the amount of magnetic field needed to cancel the superconducting property increases. Suppose if you test like this 6 Kelvin, 5 Kelvin and so on, means its value will be increasing 0.06, 0.07 Tesla. Like that. This is a study effect of magnetic field on the superconductor. If you study it and if you consolidate the critical magnetic field and the temperature, you will get a graph like this. See, you will get a graph like this. This is the temperature, transistor temperature. This is the critical magnetic field. Its value will be 9.5 for niobium. For niobium, transistor temperature is 9.5. The amount of critical magnetic field is how much? No. 9.5. If it is 0 Kelvin, you are reducing the temperature from 9 to 8, 7, 6, 5 and 0 K means the temperature came here. The corresponding critical magnetic field is H naught. H naught is the amount of magnetic field needed to cancel the superconducting property at 0 K. Okay? If it is K means the amount of magnetic field needed to cancel the superconducting property is less. Thus, C1. If further decreasing from 9.2 to 8 K means its value is increasing. Thus, C2. Again, further reducing. 7 means here 7. Corresponding value is this one. Thus, C2. Sorry, C3. Like this, if you reduce the temperature, the amount of magnetic field is increasing. So this graph gives an idea that as the transistor temperature decreases, amount of critical magnetic field increases. So at any temperature, we study only 9.5, 8 and 7 Kelvin any temperature T, the amount of critical magnetic field needed H is equal to H naught 1 minus T squared by Tc squared. This is the temperature that we need. It may be either 6 or 7 or 8. This is the transition temperature. Its value is around 9.5. So it is known. It is our wish. H naught is already decided. When the same material is kept at 0 K, what would be the critical magnitude? It is the maximum value. We just put it here. If you put it, you can find the critical magnetic field at any temperature. Maybe 7 or 8 or 6, whatever it may be, you can find the correct value for the critical magnetic field needed to cancel the superconducting. I hope that you are clear. Yes, sir. Nice. Thank you. Is that once you induce a current in a superconducting ring, the current will persist for long time. That is called a persistent current. Then it be a superconductor ring, niobium, vanadium, tin, lead. These are all the superconductors. It will act as a superconductor when you maintain a temperature T less than Tc. If I use mercury means its consistent temperature is 4.2 K. I said only the niobium value is 9.5. 9.5 or maintaining temperature let it be 6 K. Less than. The system maintaining temperature 6 K, which is less than 9.5. So the niobium ring is in superconducting state. Now current is induced to this once means the current will prolong for more than n years. Because once the current induced means they will go on. Once we kick a ball, there is no resistance with the ball on the ground and the air resistance also 0. Will the ball stop? The ball will not stop ever. Because there is no resistance, air resistance 0. The friction between the ball and the earth also 0. So once it means there is no energy loss, the ball will go on. In the same way, once current is induced means the between person means current is nothing but the movement of electrons. It is movement of Cooper pairs. They are going inside the ring. There is no loss of energy. That is why once current is induced, the current will persist for more than 2 or 3 years, and that is called a persistence current. I hope you are all very interested to study about the superconductor. Once a superconductor is given to you, you think that we can use this conductor to pass any amount of current that we like. That is true. Too much of anything is nothing. In the same way, if it is a superconductor, it is a superconductor. It is kept in a system. The system temperature T is less than Tc. What is this? Superconductor. So the superconductor is a superconducting cell. You like to pass current through this one. Let it be 2 ampere, 3 ampere, 4 ampere, 5 ampere, and so on. For a particular value of current, the superconductor lost its superconductivity. Let it be for next value. It may be 20 or 30 any value. For that particular value, the superconductor will lose its superconductivity means that is the critical current. Suppose if it is 20 ampere. It is 20 ampere. If you give that much value, the superconductor lost its superconducting property, even though the superconductor is kept below the transition temperature. So, you should not give current more than 90 ampere. For example, here, for study purpose, I don't know the correct value. If it is 20 ampere is the critical current, you have to give only 90 ampere. Then only the superconductor will show its superconducting power. Once if you give 20 ampere means you lost its superconducting property, even though it is below its transistor temperature. So this is for the critical current. The critical current can be calculated easily by using the formula IC, critical current is equal to 2 pi R into HC. It is a constant. It is a constant. R is the radius of this wire. So you might know the radius. By using the screw bar, we can calculate the diameter. Half of the value becomes radius. Then HC. Suppose for particular value, for last 2 minutes before we studied about the critical magnetic field for 6 plus last 6 Kelvin, 7 Kelvin, 8 Kelvin. In the same way, if you maintain the temperature K, it is 9.5 K. We can calculate the HC using the formula HC is equal to H naught 1 minus T squared by Tc squared. Now, so you know HC or pi and 2. By knowing that, you can find critical current. You need not worry about how much current you have to give it. Understand? Next one interesting character is Josephson effect. We might say that yes, you know very well that plastics, rubber, wood, polythene papers are all the insulators. Through them current will not pass. Okay, but superconductor can conduct electricity even they are separated by a small insulating layer. See, if it is a one superconductor, vanadium superconductor 1, another superconductor 2. These two superconductors are separated by a insulating medium, thin insulating medium. Thin insulators. In a normal conductor, current will not pass from one conductor to another conductor, but they are all superconductors. If we separate two superconductors with thin layer, thin insulating layer, Cooper pair can penetrate. Cooper pair can penetrate from one superconductor to another superconductor. This is what called Josephson effect. What is Josephson effect? He found that superconductor conduct electricity from one superconductor to another superconductor, though they are separated by a thin insulating medium. This is called Josephson effect. Okay, please consolidate the information what we studied so far. In this class we studied what is superconductor. Just one. A superconductor is a conductor which lost its resistivity at a particular temperature, and the temperature is called the critical temperature. What is TC? Transistor temperature. It is a temperature at which the resistivity disappears or a superconductor. Take case. Critical magnetic field. It is the amount of magnetic field needed to cancel the superconducting property even though the conductor is in below the transition temperature. In short, it is the amount of magnetic field needed to cancel the superconducting property of a superconductor. Next, my question is that for mercury, transition temperature is 4.2 Kelvin. For niobium, transition temperature is 1.8 K. From these two itself, you might understand that this is 0 K. 0 K is minus 273 degree Celsius. 4 K means 1, 2, 3, 4 K here. 4 K means minus 269 degree Celsius. Next, niobium. Let it be 10. 10 means 4, 5, 6, 7, 8, 9, 10. 10 means here 263 degree K. 263 degree Celsius K. That means the transition temperature is coming forward direction. Lowest value compared to greater value. If you come in this section, how to bring the transition temperatures around room temperature. What is room temperature now? The room temperature around 30 degrees Celsius. Let me just think about it. Minus 273 going on. Here 0 degree Celsius. 0 degree Celsius is 273 K. Room temperature is 30 degrees Celsius. 30 degrees Celsius. Here then in terms of Kelvin, 303 K. So the transition temperatures must rise from lower to higher, and if come to around room temperature means it is a great revolution in the science. At room temperature we are not getting the transition, we are not getting the superconducting phenomena of a superconductor. We are attaining only in this range. So scientists are trying, they are succeeding by doing some effort. For example, by giving pressure, by giving stress, by adding impurity, they are finding the transition temperature around 125 degrees Kelvin. 120 degrees, it will come here by changing the pressure, by giving the stress, by adding the impurity. They are obtaining the superconducting phenomena around 125 degree Kelvin. This is a welcome one. In future, there may be a chance to exist the superconducting property even in the room temperature. Okay? Yes. The last one. The scientists called Mason found some effect. Called this Mason effect. Let it be a superconductor. Linear system. Its temperature. It is superconductor. Tc with the transition temperature and T with the temperature of the system. When T is greater than Tc, with the superconductor, so its superconducting property or non-conductor, because T is greater than Tc. It is Tc is 9.5. T is greater than Tc means it is around 10. No? So it will not be a superconductor. If we keep North Pole and South Pole here, magnetic flux pass through these rings and enter into the South Pole. As the magnetic lines enter in the superconductor ring, it will have magnetic induction attracting property. So B is not equal to 0. Attracting property, magnetic induction not be 0. As the lines, magnetic lines are entered into the ring, it will have magnetic property. When the condition is like that, and T is greater than Tc. Suppose if you reverse the condition, here Tc, here T is less than Tc. That means you are maintaining a temperature around 6 K. If you maintain here, superconductor, north pole, south pole, the magnetic flux will not enter into the superconductor. The magnetic lines are excluded away from the lines entered in this superconductor will be excluded. This is found by the scientist Meissner. Only by changing the temperature. When the temperature is greater than Tc, lines are entering. When the temperature is less than Tc, the lines are excluded. This is called Meissner effect. In this case, there is no lines entered into this ring, so it does not have magnetic induction. It will not have magnetic induction. So B is equal to 0. The attracting property of the superconductor is 0. That means a superconductor acts as a diamagnetic one when it is in superconducting state. This is also a superconductor. It is not in superconducting state, so it is not actually a superconductor because B is not equal to 0. Here, the superconductor is in superconducting state, so its magnetic induction is 0. That means a superconductor acts as a diamagnetic one when it is in superconducting state. Okay, thank you.